and around and around, right? You have to actually lose stuff to fall into a black hole. Most of it has to lose energy somehow, right? And then it falls in, right? Okay. Now, your brain is still relatively intact, I believe, with this model. Yes. Okay. So let's forget about all that and not have your brain be intact. Okay. And let's bring up the notion of Einsteinian relativity. Okay. So that was Newton, right? Now let's go and talk about Einstein. Right? And I say Einstein because that's how you pronounce the name actually. Okay? Yeah, the ST is, so it's Stel and Stein up here in the front row. Okay? Yeah, there we have it, right? Okay? And I just say Einstein because I had a German student that every time I said Einstein, he said Einstein. And that just, yeah, cured me, right? Okay, now, here is the notion with Einstein is that this idea of force at a distance is all well and good, okay? But really what's going on is that the force is actually being caused by the curvature of space. Okay, so imagine, yes, okay, but this is not hard, this is a very accessible concept. Actually solving it is very, very difficult, okay? Requires using Riemannian four-dimensional geometry. But here's the notion, okay? Let's go back to 2 dimensions because it's very hard to picture curved space in 3 dimensions, which requires a fourth, right? Okay, so let's go to a 1-dimensional world. Yes, in a 1-dimensional world, things have only length. Yes, okay. I can take a 1-dimensional world and bend it in a way that they cannot comprehend and make. And how many dimensions does a circle require? 2 dimensions. I can now create something where if you go in line in any direction, you end up sort of back where you came because of the curvature of the space, right? What happens to you has changed, right? And you're going in a straight line, well, it's not really straight, right? It's curved in a dimension that you cannot comprehend. It brings you back to where you started. That's weird, isn't that weird? That's a little weird. Now, let's imagine a 2-dimensional world. Length, width, no height. Voila, okay. This can be bent, yes? But to bend a 2-dimensional world requires 3 dimensions. There we go. Okay? And so if we do that, if we actually bend a 3-dimension or a 2-dimensional thing, we can come up with a surface where because of its curvature, we end up going in a circle. Yeah? Isn't that weird? We think we're going straight, but really because of its curvature, right? I don't know. I don't know. Okay, so we can't picture it because my graphics processor does not handle 4-dimensional stuff, right? I'm like, can't do it, right? Smoke just comes out of my ears. But Einstein realizes that he can account for the force of gravity by just talking about curvature of space, right? So how is that possible? Well, here's how it's possible. Let's take this room. Let's throw everything out that door, all the desks and all these countertops. Let's rip them loose, kind of like One Flew Over a Cuckoo's Nest. Throw them out the door. Anybody see that movie? Brilliant movie. Okay. Stanley Kubrick movies. You have to see them all. Okay. They are disturbing and powerful. But anyway, we throw everything out the door. Yes. The room is now empty. We fill it with water this high. Are you picturing that? We have a clever system of catwalks and dog walks above the water. We stretch a sheet of rubber across the water. Are you picturing this? We have a very large water bed. Yes? And if we place a bowling ball on that sheet of rubber, it depresses the rubber, doesn't it? And makes a bell-shaped depression. And by bell, I don't mean like Liberty. I mean like the end of a trumpet or something like that. Yes? Are you picturing that? Okay? So it's shaped like this. In fact, its shape is really 1/r is what it is. Okay? It's kind of like a thing like that. Right? So by curving space, imagine if you had such a curvature, couldn't some object like the moon or a marble, couldn't it roll around in that bowl? Kind of like those things you drop the coins into and they go around and around and around, yes? Yes, yes. Okay, in fact, I have just such a thing for just such an occasion. Okay? This is shaped the wrong way. It is shaped, really the thing should be shaped this way, but this proves the point that we can make something go in a circle by curving the space through which it's moving. That's kind of cool, isn't it? What's funny about this is that the period does not really depend, if it's a parabola, on how high up the wall it is. But if it's shaped like this, if it's like level surface, And then, you know, like that. Okay, and then here is this object that we've placed on it, right? Okay, if it's shaped like that, then you orbit fast when you're close, more slowly when you're farther away. And in fact, the slope gradient of that line is how much force you have acting on you. We know that, don't we? Yeah? Okay, just from inclined plane stuff. Right, so out here it approaches level. Right, and then this is sort of interesting because it explains all sorts of really cool things. But first off, let's see that it explains our orbit, right? Imagine this, if I had a marble on an elliptical trajectory, wouldn't it, as it rolls down into that depression, go faster? And as it comes out, go slower? Faster, slower, just what we experience, right? Okay, so think about that. I'm just going to hit the R key. Okay, look at that thing. It falls down. It's falling down in, it speeds up, it goes back out, it slows down. That explains it, doesn't it? It's almost better, isn't it? Yeah? So that's one thing it explains, right? The second thing it explains devilishly well is this concept of escape velocity. Escape velocity is what speed you have to leave a surface so that when you roll up here and you get to the level part, which by the way occurs at infinity, technically, right? We could just say very far away, it stops, right? So escape velocity is the minimum velocity that won't roll back down into the depression. So if you shoot something off the surface of the Earth and the Earth didn't have an atmosphere, right? Or from the moon, there we go, right? And you shot it too slowly, it would go up and come down, yes? Up and come down too fast, and it would go out here, and it would be trucking. It would be infinitely far from the moon, and it would still be trucking. That's too fast. So the escape velocity is that minimum speed that you need to get yourself up here, put it up onto the green, and it stops, right? And the green is frictionless, so figure that one out. It's a calculus thing. It's weird, okay? So that's escape velocity. Very easy to think about it here, isn't it? Yeah? Okay. Yeah, the initial velocity that you have. Yeah. This is, see here, this is not the escape velocity. Like, yeah. Right? Much slower than that, right? Yeah, something that doesn't come back, right, is the escape velocity, the minimum one that does that. And then the second thing this explains really, really well, okay, is a black hole. Black holes aren't necessarily massive, they're just small. So think about this object, it just fits in this bell where it fits. The Earth has this size, but if the Earth were compressed and made into a black hole, which would require like a deity or something like that, right? It would just get small. It would get small and it would fit down in this thing very, very low, wouldn't it? Think about that. If we make the Earth the size of a marble, which is what we'd have to do, right? It would, how far down would it go? Well, really far down. In fact, the sides of this would be so steep that light couldn't climb out. And that's what defines a black hole. That's kind of a neat explanation, isn't it? Okay. So here's the funny story, right? Einstein is doing this, and general relativity is the theory of gravity. It's the classical theory of gravity. We don't have a quantum one yet, right? Okay, it is, I mean, it's undisputed. It's a beautiful thing, right? Einstein is trying to figure it out. He can't figure it out, okay? Because physics is sometimes too hard for the physicists. The math is, right? But he's trying to figure it out, and it turns out that Riemann, okay, has come up with a four-dimensional geometry. Mathematicians do that. They're just like, here's four-dimensional geometry. Well, that's great. What would you ever use four-dimensional geometry for? I don't know, but here it is, right? So he writes this book. He's like the Euclid of four-dimensional geometry. Writes a book. It's in the library. Einstein is trying to deal with four-dimensional geometry. Has no clue how to do anything with it. And one of his friends says, hey, read that book, right? Einstein reads it. He's like, ah. And he uses Riemannian geometry to explain general relativity. Isn't that a beautiful thing, right? There's something called set theory. It's a very, I don't even know what it is, except for its name, right? But it's helping physicists understand how particle behavior works. So it's, you know, it's kind of a cool thing. I think that's a cool thing to have mathematicians off here doing these random, bizarre, theoretical things. Physicists going, okay, I want to read that book. Yeah?
Okay, I have a question. It's kind of really not pertinent, but if light's like a wave, right?
If light is like a wave.
Then how does it travel through space since there's no matter in space?
Yes, right. So it's not a mechanical wave, right? So light is a crazy bootstrapping thing, right? If I have a magnetic field here, if I take a magnet and I move it away, the magnetic field collapses, but the energy that was that magnetic field cannot go nowhere. It cannot be destroyed, right? So a collapsing magnetic field creates an electric field in space, and that looks around and goes, hey, nothing here to make me, so it collapses, right? So these electric and magnetic fields, right? A magnet works in a vacuum, so they have to have a magnetic field. They contain energy, and then they just have this thing where if you destabilize them, they just oscillate like that and go through the vacuum. It's a crazy thing. Yeah, Lizzie's got a question.